Good morning. Thank you for being here on this kind of blustery day. I don't usually record recitations, but I am going to record this one because I'm not sure if we're going to have recitation some of the upcoming days. So I do not like recording recitations. I have to move the camera. It never comes out right. But anyway, that's why this is on. I do appreciate you being here. I know the weather's kind of crazy outside. So let's talk about, first of all, what's going to happen. If you haven't done so already, turn in the solids lab, the rough draft of your class presentation paper, and if you'd like to turn in the exam analysis, turn that in as well. And then now problem set number 5 is up. We'll talk about that before doing quiz number 5. And there is no actual lab today, all right? Today we're going to have a take-home lab. It's a take-home version of the lab that we were going to do, a take-home freezing point lab. And so by 10 o'clock today and stuff, we will be done and we'll be out of there. We're going to talk about what's going to happen next week, Tuesday morning at 8 o'clock, which is taking the first or second exam. Woohoo! And it's chapters 9, 10, and 11. So chapter 9, gas laws. Chapter 10, talking about a little bit of solvents, how they turn into solids, gases, phase diagrams, crystal structures. And now chapter 11, which is over solutions. And we'll talk about all these things here in just a little bit. When you come next Tuesday morning at 8 o'clock, all right, a couple of things to bring. Definitely bring a Scantron with 100 questions total, like before. Definitely a calculator and a pencil. You'll take the take-home freezing point lab, bring it along. Exam prep 2 will be due, so just like before the first one, there was a double-sided handout, about 5 questions, question, answer, show your work, and please let me know if I can help on those, because that's totally fine. We will have a study session and lecture, although now, because of yesterday, my schedule's a little messed up, so I'm just going to put soon right now, and so I will announce more as it comes down. I'm hoping by Friday to do it, but again, we kind of have to see what the weather's going to be like. If you can't wait, you have to do it now. I do have like lectures from last year and the previous year, which are similar, all right? You know, they won't be quite the same, but they will be close. And if you'd like to email me, that would be fine. If we do have class outings, then I'll be emailing them around. And then definitely next Friday then I should be able to return the midterms and stuff if that all happens. Now, the lab itself is a double-sided sheet, so there's nothing to type or anything like that, which is cool. This is more of like a data analysis kind of lab where it gives you some information. You'll plot it in Excel or a program like that, so you'll staple that to the back and then fill out the answers, therefore, from within. And some of the questions today will be similar to the lab, and I'll try and give you a heads up and stuff as to which ones that is. Your problem set today, you will turn in to me, and I will return to you before you leave today, so you can have it back. So write all the notes over it and stuff like that that you want. It should be good. And oh, I think I forgot to mention, it's a take-home quiz. Woohoo! Now, some of you knew this already and you'd ask me, okay, but some of you didn't. Well, anyway, sorry to be so cheesy. Take-home quizzes are important sometimes when things get kind of crazy, and my goodness, this is definitely the week where everything's gone crazy on us. So today's is going to be a take-home quiz. So let me add this to the list of things that you must bring next week. When it comes to take-home quizzes, I will not allow you to turn things in late. So you can leave everything else at home if you have to, but don't forget this, because after the quiz, after the exam is given, this will be worth 0 points. Now, we haven't officially had a take-home quiz like this before yet, so I want to talk about it. I love it when you guys work in groups, all right, and anyone from the class you can work with, other Chem 222 sections and stuff like that, but please do not ask the tutors, don't ask your friends from MIT and stuff like that. Just work on this internally. I want to make sure that you know what the questions are asking, but I will not help you with these problems either, all right? So this is something I want you to try and strive for a take-home quiz today. 20 points on the front page, 20 points on the back page. What do you think happens if you get more than 20 points on a 20-point quiz?
Extra credit.
This is a serious amount of extra credit today. And this will also give you some incentive then for trying to keep with this stuff, because it's coming fast and hard right now. I know, man. And lecture now has been screwed up. So, 20 points on the front page, 20 points on the back page. I love it when you guys work together, check your answers, watch the sig fig, stuff like that, all the things that your instructor likes. Make sure you turn it in next Tuesday at 8 a.m. I won't take these late. So today, all right, sit back, relax. All right, number one, because I know things are kind of crazy. I feel it too. Every time it snows, I'm like, oh my gosh. But anyway, Professor Reed probably don't need to hear about it. Try to sit back and relax and ask the questions you want to today. We're going to basically have some small lecture over some new stuff because we haven't seen it, man. And I want you to ask questions. And at the end, then, I'll take your problem sets real quickly. I'll grade them real fast, and I'll return that and last week's work to you before you leave.
So next Tuesday is the exam, the Tuesday after that is the presentation.
That's right. We'll talk a little bit more about that next week, but yeah, that's right. It's kind of rock and roll times right now, man.
Yeah.
So, any questions like that? That was a good question. All right. So again, knowing that it's a little weird that I'm going to be recording this, I'm going to move the recorder around as we go through and stuff. Just in case, again, we have any snow. Chapter 13, I have had time to lecture on it, but chapter 4, thanks for playing, that's the old book. Chapter 10, sorry, I think I've done pretty good in lecture, but chapter 11, I hardly started at all. So there are 5 equations from chapter 11 that are kind of important to know. And those 5 equations have names. Henry's law is the first one, which I think is question 12, although I'm not totally sure. Then there's what's called Raoult's law, which is about a depression of the solvent. Oh gosh, vapor pressure. Sorry. Oh, caffeine hasn't kicked in yet. Sorry, it's called vapor pressure depression. And this is a thing of solutions we'll talk about. Then there's what they call boiling point elevation, freezing point depression or freezing point lowering, and osmosis, all right? And all 5 of these are properties of solution when you have a solute and a solvent together to make a solution. So if we have pure water, none of these apply. If you have pure acetone, none of these would apply. But if you put acetone in water, where acetone would be the solute and water the solvent, all of these could apply. And we'll talk about these as we're going on. So chapter 11 is just an extension then of our discussion of gases, liquids, and solids and how they interconvert. These are the properties now of solutions that we're going to get into. Now along the way, there's some new characters here like pi and k's and little m's and stuff, and I'll talk about those when we get to the problems. But as we go through it, kind of think about this in the back of your head. Yeah.
What's the character to the left of the C?
This one?
To the left of the C.
Oh, I. It's a little tiny I. That's called the Van 't Hoff factor, and we will talk about it today, I promise, man. This little I right here, you can see pops in several places.
Oh, so it's the same.
That's right,
Sorry,
exactly.
I thought it was a special character.
No. Please ask. I have horrible handwriting, and then so you have get out of jail free card to ask. So. All right, but let's start on the graph on question number 1. These graphs right here are part of a bigger phase diagram. Now, in a phase diagram, you have essentially pressure and temperature on the y and the x-axis, and the phase diagrams, as we'll talk about a little bit later, look kind of like a y. Actually, this part of the y is usually more curved. Let me redraw it like that. And on question number 1, we're kind of looking at just that part of the phase diagram. So it's the interface between where there is a liquid, which is the part in the middle of the y, and a gas, which is the area on the far part of the y. The solid, which isn't showing on question number 1, would be on the left-hand side. So on question number 1, we're seeing just like the right-hand side of that phase diagram. They call them vapor pressure diagrams and stuff, different things. But anyway, to read them, pretty much it's pretty chill. First one, it says, what's the equilibrium vapor pressure of diethyl ether at room temperature 20 degrees? So you can see that of these curves, each one of them has like an associated piece with it. Diethyl ether is the one on the far left. So if it wants the pressure, just go to 20 degrees on the x-axis and go straight up until you hit the line. Then go over to the left side where the pressure is red. That looks like that's a number of 400 millimeters of mercury. So you would say that the vapor pressure of diethyl ether at that point is 400 millimeters of mercury. And again, the studio audience, sorry, this is kind of what I'm doing right there, going up to 20. All right. I hate using the camera at this part, sorry. Anyway, number 2, it says place diethyl ether, ethanol, and water in order of increasing intermolecular forces. So diethyl ether is polar. That would be a dipole-dipole intermolecular force. But ethanol has an OH on it, so it's more than dipole-dipole. What do we call that force? Hydrogen bond, that's right. Hydrogen bonding is stronger than dipole-dipole. Water has 2 hydrogen bonds, 2 OHs on it, so water is considered even stronger than ethanol. It has even more powerful. So notice that diethyl ether is first, ethanol next, and water last. That is the order of increasing intermolecular forces. The vapor pressures actually are getting larger as the intermolecular forces increase. So it's a subtle impact of how the IM forces do affect these kind of things. And then finally it says, if the pressure is 400 millimeters of mercury and the temperature is 40 degrees, which of these are liquids and which ones are gases? So remembering that to the right of the curve, that's when you're going to get into the gases, but if you're left of the curve, you're going to be in a liquid phase. So what I would do for this one is I would start, for example, at 400 millimeters of mercury and just move your way right. And you can see as you move your way right, you cross through the diethyl ether curve. That means you're going from a liquid to a gas for diethyl ether. But at 40 degrees Celsius, which is just to the right of that dotted line there, we have not gone through the ethanol or the water curves. So that means that those two are both liquids at 40 degrees. All right, we haven't crossed through that barrier yet to see what's happening. Any questions on that? Okay. So question number 2, it says if the intermolecular forces in a liquid increase, what happens to the boiling point? Boiling point also increases, all right? Intermolecular forces go up, the boiling point increases too. It takes more energy to break those intermolecular forces as they get stronger. So B, if the intermolecular forces decrease, the vapor pressure actually increases because if there's fewer forces holding those liquids together, it's easier for the liquids to get into the gas phase. So if the forces are decreasing, your vapor pressure, which is just the pressure of the gas molecules over the liquid, that's going to go up. If the surface area decreases, in theory, the vapor pressure should not change. If we have, say, an example of Crater Lake versus a little pool of water here in my sink, and the temperature's the same, and it's pure water, we'll assume, in theory, we should have the same vapor pressure. Now, of course, there's lots of variables with that. If there's pollution, stuff like that, in either one, that'll affect it. But in theory, any size surface area, you should have the same vapor pressure. And finally, if the temperature increases, the vapor pressure will increase as well. On this part, all of these, the things are increasing as the temperature gets bigger. Pressure goes up as the temperature goes up. That's part of the gas laws. So that means increases. So on that one, it goes increases for A, increases for B, does not change for C, and increases for D. Any questions on that? Okay. The next one is an example of a full phase diagram. And all of these have pressure on the y-axis and temperature on the x-axis. And as you can see here, there is a Y. It looks a little bit different than the Y I just drew, but the ideas behind it are the same. You're going to have solid on the left of the Y, liquid goes in the middle of the Y, and gas on the far right of the Y. And then along there you can see how you have a pressure axis and a temperature axis. Of most important to us is you can see that there's a 1 atmosphere pressure. And there's like a dotted line that goes all the way over there. And then you can see the gas goes over there. But the temperature axis, the biggest temperature on there is minus 105 degrees Celsius. So this is for xenon, all right? What phase is xenon found at room temperature and pressure? Gas, that's right. If you look on the periodic table, all the red elements on this one and other ones, those are all gases. It's a noble gas, all right? So we expect it to be a gas. Excuse me. We expect it to be a gas, and if you go over on 1 atmosphere on this graph all the way to the right where room temperature is, it would be way over by India over there. It'd be a long ways. So we're passing through the solid-liquid interface, the liquid-gas interface. Should be just gas. Yeah.
When we're talking about room temperature for that, are we talking like -20 or not negative, but 20 Celsius or?
Usually it's considered 25 and
Okay.
stuff, but 20, 25, not a big deal. I use 25, Nathan, because the thermodynamics, the delta H's and stuff are usually quoted at 25 degrees Celsius and stuff. But as you can tell from that last problem, sometimes people think it's 22.
Oh.
Good question, Ryan. Other questions? Okay. Second one. So the phase of xenon's found at room temperature, 1 atmosphere pressure, gas, absolutely. And you can look at the periodic table, or you can just read this diagram over to the far right. Now, if the pressure is 3/4 of an atmosphere and the temperature is minus 114 degrees Celsius, what phase is xenon? So on this one, what I would do is go to your graph and go up to where you think 3/4, 0.75 is, which is halfway, of course, between 0.5 and 1. And then you can go over to where you think minus 114 is. And to me, that looks like you're in between the Y. It looks like that would be a liquid phase, all right? Now, this is not the world's best graph. And if you read that and you think, oh, you're on the solid liquid line or something like that, it's okay. The idea of this problem is being able to read a graph and then figure out what you think is the right phase. Does that make sense? Okay. If you measure the vapor pressure of a liquid sample and you find it to be 380 millimeters of mercury, which is half of an atmosphere, what is the temperature of the liquid phase? So on this one, first of all, realize that 380 is half of an atmosphere, which is what our y-axis is coordinated. And if you go over at half of an atmosphere, there's a pretty narrow range of liquid temperatures right there. Anything between that range is okay with me. So to me, it looked like it was about minus 119 to minus 117. So if you have a number in that region, that's totally fine. Jesse uses minus 116. Hey, that's okay. That's close enough for my hand grenade. A little bit of sig fig uncertainty because of the cheesy graph. As long as you're about there, that's cool. Questions on that? Okay. D, what's the vapor pressure of the solid at minus 122? Now, all substances can go straight from a solid to a gas. Water is not one of those at our standard conditions, all right? We're used to seeing it as a liquid. If we cool it down, it becomes a gas, and we heat it up, it becomes steam. But carbon dioxide is an example of this. If you go to Fred Meyer's and you buy their dry ice and you bring it home, after a while, woo, it goes away. That's the solid CO2 turning into a gas. So every one of these phase diagrams is different for every compound. But in xenon's case, excuse me, if you go to what's about half of an atmosphere and you go over, and then you go straight down, that's the temperature you're looking for. So if you go where you think is half of an atmosphere and you go right until you touch the line, and then you go down, that's the temperature you want to quote for this part. To me, it looked like it was about a minus 122 degrees Celsius. But again, plus or minus a few degrees is okay right there. This last part is kind of interesting. You can actually tell from the phase diagram if the solid or the liquid phase is denser. And if you look at xenon's solid-liquid line, which I've drawn right here, the solid-liquid line is increasing up and to the right. Is this a positive slope or a negative slope?
Positive.
Positive, that's right. If you have a positive slope like this one, that means that the density of your solid is greater than the density of the liquid. So if you had solid xenon and you put it in a liquid xenon bath, I was going to say drink, but that sounds really strange. So put solid xenon crystals, if you will, in liquid xenon solution. All right, the solid will sink to the bottom. And most compounds, that's what happens. The solid phase goes to the bottom of the liquid phase. But of course, why we bring this up is because water does not have that. If you put an ice cube in water, the ice cube floats. So when you look at the solid-liquid interface line for water, it has a negative slope. It's, if you will, increasing up and to the left or down and to the right. If there's a negative slope, then the liquid phase is more dense than the solid phase. So ice cubes floating on water is actually a pretty rare phenomenon. There's only a couple of compounds that do that. Most of the time, the solid will sink to the bottom. Negative slope means that the liquid is pushing on the solid. I like to think the liquid is pushing over into the solid, so it's more dense. That works for me. Anyway, but if the slope is positive, then the solid is pushing into the liquid. That means the solid is more dense than the liquid.
Are there equations that we're going to go over that would determine a graph like this?
No, this is as much as we'll do. But in physical chemistry, which is third year, you bet you can slope this and stuff like that, and derivative and stuff. So, but we're having enough fun as it is, man. Good, excellent question. So the equations do exist, but that's a friend of the class. Okay. Other questions on that? Indeed.
I think I missed the explanation for D.
Mhm.
That one, could you
Yeah.
say it again?
So look at the graph again and just go where the temperature is minus 122. All right, so this line right here is about minus 121, so it would be just to the left. I want to make sure I'm telling you the right thing. And then just go straight up, Indy, to where the line, the solid line is, and then just move over to the left, to the pressure side. So to me, that looked, 0.2, 0.25 atmospheres, something like that.
Okay, yeah.
Good. And again, that's really only for when solids go directly into gases. For water, that's not as big of a thing and stuff. Other questions? Okay. Number 4 and number 5 are a little bit of review, but they are relevant to what we're talking about. In chapter 10, excuse me, we have lots of problems where we're talking about solids by themselves, like lab, liquids, how you go from solids to liquids. And along with that, we need to talk about the energies required to make these transitions. And there's basically 2 parts to number 4. And the first part is an MC delta T problem. And this is something from Chem 221. If you have, say, liquid water, all right, and you want to heat it up to make steam for tea or something like that, you have to raise the temperature of your liquid water. So let's say we start at room temperature, 25-ish degrees, and we went to 100 degrees. Delta T would be the change in temperature. That would be 100, the final temperature, minus 25, the initial temperature. Your delta T can be in Celsius or Kelvin. Either way is fine. The magnitude of delta T will be the same in both ways. M is the mass of the water in grams that you have, and C is the heat capacity. And for liquid water, that number is 4.184. That's for liquid water, and that's the only heat capacity that I want you to know / memorize. We used it a lot in Chem 221, and we'll use it a lot again here now. So this is the energy required to heat a substance, but you're not changing the liquid to a solid, or you're not changing the gas into a liquid or something like that. So I call these energy changes, but no change in phase. And that just means you're not turning your solids into a liquid or your gases into liquids, all the same phase, like liquids. But there's also another kind of Q, and in Chem 221, if you took it with me, I called it mass, in quotes, times heat of something. And this is very laid back, and I apologize. Mass can be grams or moles. And the reason that it can be both is because it depends on the heat of something. And the heat of something will have a name like heat of vaporization or heat of sublimation, or there's different names like this. So in this problem, you're going to have two types of Q calculations. And one of them will be heating up your sample. And that's what this calculation is right here. And the other one, we're going to have a heat of something, which I believe is the heat of fusion in this problem, 11.3. We're going to see what's happening. So we're taking some silver. The silver is a solid. We have 5 grams of the silver. It has a heat capacity C, which you can see is given, nothing you have to memorize, of 0.235. And we're heating it from 962 from 25 degrees Celsius. So 962 minus 25 is how this person got the 937 number. They could have just as well done it in Kelvin, and they would have had the same number right there. A delta T in Kelvin is the same as a delta T in Celsius. So when all is said and done, you'll get a number which is about 1100, and the units of this right now are joules. And that's the energy to heat your 5 grams of silver from 25 degrees Celsius up to the melting point, which is 962. Questions on that part? Okay. Now, for the second part, we have this heat of fusion, which is the heat required to melt this thing. And you can see here that this number is 11.3, and it's kilojoules per mole. All right? Now, I love it that this person, first of all, converted the kilojoules into joules. The number right here, 1100, is joules. So you want to make sure you add apples and not apples and oranges. And what that means is if we have joules here, we better have joules here. Or you could convert this to kilojoules and add it here. That's awesome. Now, the other part was close. They used Avogadro's number, which is the number of atoms in a mole, or the number of molecules and stuff like that. In this problem, what you can do instead, though, is use the molar mass. So silver on the periodic table is 107.9 grams per mole. This is moles of silver, so the moles of silver will cancel, and you've got 107.9 grams. And then in this problem, because we had 5 grams of silver, the grams will cancel out. Then if you look, you've got just joules left over. So again, right idea, but in this case use the molar mass, not Avogadro's. This number comes out to be, put a negative sign right there because we aren't vaporizing. We're not turning a liquid into a gas. We're taking the gas down to a liquid. And what was endothermic, that one direction will be exothermic the other way. So mathematically then, plug this into your calculator, minus 3,330 joules. Okay. Now, Q3 is going to be another MC delta T, but our heat capacity will be a little bit different. So I'm going to start like on number 1, 20 grams, turn it into moles. The heat capacity for the liquid is 72.3 joules per mole Kelvin. And my delta T, the final temperature, negative 40, I'm going to subtract the initial temperature, minus 29.8. When you put all this together, minus 122 joules. So the total of all of these will be just Q1 plus Q2 plus Q3. They should all be the same sign. Again, number 2 is a little tricky because it's not vaporizing, you're condensing. But anyway, minus 4.80 times 10 to the 3rd joules, or minus 4.8 kilojoules. Okay. So at number 4, we did MC delta T plus a mass times delta H. Here we're just doing the same kind of process, only there's one more piece on the end now where we're additionally cooling the final state down a little bit further. Yeah.
So, just so I'm getting it, like,
Yeah.
Q1 is going to be where you're, say, it's going to be the slope part of a graph, and then Q2 will be the flat part, and then Q3 will be the other slope.
Absolutely, that's
Okay.
right. What Nathan's talking about is you can absolutely plot these kind of things. So this would be like a temp axis, and this would be like an energy, that's right. And so we start off with some amount of energy, and it goes down from 40 to negative 29.8. So this would be the MC delta T. And then it is flat right in there, absolutely. This is the M delta H part. And then there's another flat slope part when it gets down to negative 40. This is the second MC delta T. Well done, yeah. Sometimes this helps me to think about it, so that's why I'm glad you brought that up, man. I like using timelines or graphs like this. And again, Nathan totally nailed it. If you have a phase change, the temperature is constant, all right? You'll have temperature changes on the other sides, but the actual phase change is going to be the same. Other questions? Yeah. Go ahead.
So phase change is just mass times sum.
That's right. That's right. At any time you go from solid to liquid, liquid to gas, gas to solid, any of these kind of things, that's when you'll have this M times delta H. That's right. Other questions? All right. Number 6, which I didn't put up here, is an example of another one of the unit cells. And number 6 should look familiar as the body-centered cubic cell. There's an atom in the middle of the tungsten stuff, so you can do it from there. It says how many tungsten atoms are there per cell. Body centers always have 2 atoms per cell, 1 in the middle, and the 8 times 1/8 around it. And then finally, if you have a body-centered cubic, the radius, well, let me put it this way, edge equals 4 times the radius divided by the square root of 3. So if we have an edge, 316.5 picometers, you can solve for the radius. You would take 316.5 times the square root of 3 divided by the radius. I had 137.0 picometers. So you just rearrange that equation for the radius. Now, on number 7, this is kind of like what we did in lab last week too. This is calcium. It's in a face-centered cubic system. So face-centered cubic means 2 things. It means that you have 4 atoms per cell. And the other thing that we'll run into down here is that the edge equals 4 times the radius divided by the square root of 2. So face-centered is 4r divided by square root of 2. Body-centered is 4r divided by square root of 3. So on number 7, it says we got a density. What's the radius of the calcium atom? Good. And so again, what I would do is start over here with atoms and work your way over on the quote-unquote train track we used last week. So 4 divided by Avogadro's gives you the moles. Moles, you can then convert into grams using the molar mass, which is about 40 grams per mole. The mass comes out to be pretty small. That number looks very legit. Then you can turn mass into a volume using the density. The density is 1.54 grams per centimeter cubed. Now, when you go from grams to volume, the density is only about 1. So there will be a times 10 to the something on the volume term. And I don't know if I actually, I have 1.728 times 10 to the minus 22nd centimeters cubed. So just remember, try not to forget the times 10 to the on these things and stuff, they'll do it. Once you have the volume, you can take the cubed root of the 1.7 times 10 to the minus 22 number, and that'll give you just the edge. And the edge this person had was 5.57. Okay, good. So I had a number here that was 5.57 times 10 to the minus 8th centimeters. No problem. So make sure it's a cubed root, not just a square root. And then usually the edges are about 10 to the minus 8 centimeters on things. Anyway, once you have that, then you want to convert it over into picometers. This would give you the edge, which again is about this number times 10 to the minus 8th. If you take this number, the edge, and let it equal 4r divided by square root of 2, you can then solve for the r. You would take 5.57 times 10 to the minus 8th times square root of 2 divided by 4, or you could convert this over into picometers first. I had 197 picometers for the radius on that one. So again, don't forget the power of 10, cubed root, and then edge equals 4r divided by square root of 2 to get that radius, and then you're good to go. Cool. Questions? Okay. Number 8, which I have erased here, is an example of what's used called the Clausius-Clapeyron equation. And this is the way that people actually can find the heats of vaporization and the heats of fusion and blah, blah, blah. In a nutshell, on number 8, the goal is to essentially make a graph of the natural log of the vapor pressure versus 1 over the Kelvin temperature. Now, if you looked at number 8 and you're like, Russell, all right, don't worry. I'm hoping you can at least get the first one, because the normal boiling point of the solution is where the vapor pressure equals the atmospheric pressure. And the normal boiling point, 1 atmosphere, would be 760 millimeters. And you can see that the last value on the table on number 8 is 760. So the normal boiling point will just be the temperature at that point. The normal boiling point will be 70.3 degrees Celsius. Water normally boils at 100 degrees Celsius if it's exactly 1 atmosphere. So the normal boiling point for this dichlorodimethylsilane stuff, 70.3 degrees Celsius. Questions on that? Okay. Now, pressure can be atmospheres or millimeters of mercury. You can use either one for that one. But 1 over the Kelvin temperature, Kelvin is important in the stuff we're going to start doing. When you graph this, and I would use Excel or one of these things, you should get a nice straight line, all right? And this just screams out linear regression. Now, a linear regression gives you the best fit slope, y-intercept, all this kind of stuff for your different values. So if you saw this and you thought, I wonder if I can finally use my linear regression skills we did in the lab at the beginning of the term, and don't throw tomatoes at me, please. Y equals negative 3885.2x plus 17.949, and the R negative 0.99989 is what I came up with. Yes?
When you are using Excel and like when you put in the boxes for your X and Y, do you put in the pre-calculated values, or do you put in the equation?
When you do the regression, as long as you select the correct columns, Rebecca, it doesn't really matter. But what I would do is I would have a column first of all of Celsius, and then if you know Excel, you can quickly turn like one column into another column set of data. So you can go Celsius to Kelvin like this plus 273 and fill down. And then I would take a third column and do 1 over the Kelvin temperature. If you know about that, that's easy. But if you don't, then yeah, just use 1 over the Kelvin temperature as the first part, and natural log of P as the second part.
Okay.
And then you can do the regression on it. If you're curious about what I was talking about, if you give me like 5 minutes in my office, Excel and these programs are really cool for transporting data from Celsius to Kelvin to 1 over Kelvin temperatures, and also vapor pressure to natural log. I can show you this kind of stuff, but if you don't want to deal with that, and you know, my room is weird, just put in the 1 over Kelvin temperatures in your first column and natural log of P in the second, and that's totally cool. Okay. This number is the number that you really want to focus on, because the slope of the Clausius-Clapeyron equals negative delta H over R. And delta H is kind of what we're after right here. Now this R is the other R, 8.3145. It's similar to our 0.082057, but it's got joules instead of liters atmospheres. So if you take this number and multiply it by negative 8.3145, the delta H that pops up, 32.3 kilojoules per mole, or kilojoules. And several of you contacted me and said, oh, I'm using points 1 and 2 and I'm getting delta H of 30, and points 3 and 4 give delta H of 35 or something. That's why the slope is the best answer, because it should reflect the best guess of all those points in there. It's not just based on 2 points, you have the best ones. So I throw this in there just as two things, actually maybe 3. Number 1 is we finally get to use linear regression. Woohoo! And we'll do this a little bit more in problem set 6 too, but it's not hard, it's just a tool using freaking things. Number 2, it shows how using the regression slope gives you the best value. It's better than having just 2 points. You have all of the points in theory subjected to it. And then 3, this is the way they calculate these heats of things. Heats of fusion, heats of vaporization. They'll do something similar to this. This will be in the same class. Nathan will learn it along with why the slope of the density line sometimes is greater for solids and liquids and stuff. Yes?
So then for part B, when it gives you a pressure and then asks you to find the temperature, do you just take the natural log of the pressure and then plug it into your...
Exactly, that's right. So if I was doing this as easily as I could, all right, I would literally find natural log of 40, and it's a number, all right? Natural log of 100 would be a number. And those will be your y-axis. And then for Kelvin, it would be 1 over parentheses, 273 minus 0.4, stuff like that, all right?
Is there a way to find delta H with the equation that you gave us in the lecture?
So you can, Nathan, but it's not as good as this one.
Okay.
And that's another thing I want to point out, is if you use 2 points, you will get an answer, and it'll be about 32.3, and honestly, that's awesome too. But when you do have a bunch of data, the linear regression slope usually gives you the best of all those values. So if you don't have a lot of time, screw you, Excel and Microsoft. Yeah, definitely do just 2, but if you don't mind doing it, it does give you a better value.
Okay.
Good. Other questions? Okay. Number 9. I'm going to move this over here. We're now entering the world of solutions on number 9. And when we get to solutions, we have lots of the different things. And notice what the middle board in the front is. Henry's law, Raoult's law, boiling point, freezing point, osmosis, all right? These are really cool things that solutions do that regular solutes and solvents by themselves do not. But along the way, we need some new types of units. As you've seen in lab, the density of water changes with temperature, all right? So sometimes we went to that big handbook of chemistry physics to look up the densities, and a water temperature of 25 will give you a slightly different density than the water value at 27. It's not the mass fault, because mass isn't changing, it's volume's fault, and volume changes a little bit with temperature. So in the kind of stuff we're after, we want to stay away, usually, from those kind of calculations. Volumes change with temperature, so they're not as reliable. And we want to know more about the relative pieces of things. So on number 9, we have this table, all right? And it's KNO3, and it's CH3CO2H, which is acetic acid, and we have another compound here, which is ethylene glycol. And then next to it, you'll see these weird things, molality, which gets the symbol little m, weight percent, which I'm just going to write as a percentage, and then another one, which is going to get what's called a chi, which is an italicized X. It looks like an X. This thing is called mole fraction. And these 3 types of units, molality, weight percent, and mole fraction, are really helpful when it comes to studying the properties of solution. Now, normally, like on number 10, we use the big M, which is molarity, and that is moles of solute per liter of solution. Molarity is the king of solution concentrations when it comes to chemistry, all right? Molarity is easy, like in our lab that Vadim works at and stuff. Almost all of our solutions are molarity. We have a few weight percents, but most of them are molarity, all right? Really, really easy. But in this section, we need these other kinds of units. So on number 9, we're going to talk about these new types of units. And on number 10, we're going to see how we can take molarity and turn it into one of these, or take one of these and turn it into molarity. There's a handout in your companion that I highly recommend you check out. It's called the Concentration Unit Calc Solution handout or something like that. I can send you a link and stuff. It was in my last email to you, but I'll send it to you again. And in this handout, there's going to be more detailed analysis of how you interconvert these, how you turn one from the other. One of the big goals of this section is that you know how to calculate these 3 types of units and how to interconvert to molarity and back and forth again. So, I'm going to do an example of the first one. And in the first one, it says we have a 10% KNO3. So for KNO3, 10% means that we have 10% KNO3, and our solutions are all aqueous. What does aqueous tell us that our solvent is? Water, that's right. So on all of these are the solutes, and the solvent in all of these is water. And remember, a solute plus a solvent equals a solution. So KNO3, 10%, what that means, this is literally a grams of KNO3. And it means we have 10 grams of the solute KNO3, and if there's 10% of something, there must be 90% of something else. What do you think the something else is?
Water.
Water, that's right. So 100 minus 10, 90 grams of water. So the first thing is just being able to identify amounts of solute and amounts of solvent. So if you have a 10%, that's 10% of the solute in this case, and then 100 minus that number would be the grams of solvent. Okay? In these problems, you need to get moles of solute and solvent, and you also need kilograms of solvent. So 90 grams of water, if we divide by 1,000, 0.0900 kilograms of water. And I'll show you where we need that here in a little bit. But the other thing we need besides grams of solute and solvent is moles. So let's convert these into moles. So water is about 18.02 grams per mole. KNO3, I have to look that one up, 101.1 grams per mole. So when you figure these numbers out, 0.0989 moles KNO3 and 4.99 moles of water. So grams of solute, grams of solvent, kilograms of solvent, moles of solute, moles of solvent. If you have those 5 things, this table will fall for you. So, sound effects not necessary. Molality, which is little m, do not use big M for this and don't use little m for molarity anymore. Molality is moles of solute, which here is KNO3, divided by kilograms of solvent, which here is water. So molality then would be 0.0989 moles KNO3 divided by 0.0900 kilograms of water. Welcome in. When you throw this in your calculator, 1.10 molal is the number you would want right there. So this solution, 1.10 little m. Okay. Mole fraction is literally just a ratio of moles. It's defined as the moles of what you're looking for, which in this case will be moles of solute, divided by total moles. So I'm going to take moles of KNO3 plus moles of water in the bottom. So if you take the moles of KNO3, 0.0989 moles, and you divide it by the total moles, so I'm going to divide it by 0.0989 again, plus 4.99 moles of solute plus moles of solvent. These numbers are usually pretty small. This comes out to be 0.0194. Mole fraction and weight percent do not have any units with them. They're just either a decimal like this one or a weight percent in the other one. So here, 0.0194 would be the mole fraction. Yeah.
Is that on the molality or molarity?
This is molality.
Okay.
Yeah. We'll talk about molarity on number 10.
Other questions?
So, let's kind of review here. Weight percent, this 10% came from the fact that we had 10 grams of KNO3 and we divided it by the total mass, which is 10 grams of KNO3 plus 90 grams of water. This one we did multiply by 100%, but that's where this number came from. So weight percent, we needed grams of solute and grams of solvent. For molality, the little m, we're not to molarity like Nathan just asked, moles of solute divided by kilograms of solute. This is the one time you need kilograms. And then mole fraction is kind of like weight percent, but it's with moles. You don't multiply it by 100%, but this would be, in this case, moles of KNO3 divided by total moles. So that would be divided by moles KNO3 plus moles of water. So if you have moles of both solute and solvent, grams of both solute and solvent, and kilograms of solvent, all of these will fall to the rule. Okay, I'm not going to go over all of the details for the next ones, but I do want to show you how to get started on the next ones. On the second one, it says 0.0183 is the molality of this stuff. So, how I would start this problem, on number A, or the first part, 10%, we assumed it was like 100 grams total. On this one, I would assume 1 kilogram of solvent, which would be 1,000 grams of water. And the reason I assume that is because 1 kilogram means we have 0.0183 moles of acetic acid, CH3CO2H. So if you're given a weight percent, assume you have 100 grams. If you're given a molality, assume you have a kilogram of solvent. And then whatever number it is, that will be the moles of the solute. And from this, you can turn this into grams using the molar mass. You can turn the kilograms of water into grams of water, which will lead you to moles of water. The weight percent would be the grams of the acetic acid divided by grams of water plus grams of acetic acid times 100%. The mole fraction would be this number, 0.0183 moles of solute divided by moles of solute plus moles of water. So from these, you can calculate all these crazy things. I had 0.110 for the next one. And mole fractions can be small. 3.30 times 10 to the minus 4th is what I had for the last one. For the last one, they gave a mole fraction of 0.0599. If you're given a mole fraction for this thing, which is ethylene glycol, what I would do is assume 1 mole total. And that means you have 0.0599 moles of ethylene glycol. And that will lead you 2 grams using the molar mass. But this also means then you have 1 minus 0.0599 moles of water. If you have 1 mole total, then 0.0599 moles will be the moles of solute, and 1 minus that number will be the moles of your water. Moles of water leads to grams of water, which leads to kilograms of water, and then you can put those things in from there. So when you do that for this problem, I had 3.54 for the molality and a weight percent of 18. Now, all of these things are things you can do, but you do have to sit down and practice them, man. And it's not the most fun sometimes, all right? You know, I mean, I'm not a big Olympic fan, but even I would watch the Olympics probably sometimes. It's like, you have to do it, man, because this is it's understanding solutions. You have to figure out these types of units, and it's all algebra, and it's just figuring out which one goes which. This solution concentrations handout in your companion and online, I think will help, because it's going to have the worked examples, and then there's another whole set of problems like this where the answers are given, but it asks you to kind of figure out how they work and stuff. So, any questions on this? Okay, now, we're not done though with molarity. Molarity really is the king of the concentration units. Molarity is big M. Little m is molality. And molality is moles of solute per kilogram of solvent. All right? So there's molarity and there's molality. And you've got to use the right kind of M and stuff while you do these. So number 10, it says we have a 95% H2SO4 solution, an aqueous solution. And like we did over there, you have a weight percent like this one, assume 100 grams. So that would be 95 grams H2SO4, and 100 minus 95, or 5.0 grams of water. And what it says on number 10 is basically turn them into molarity and molality. So molarity, moles over liters, molality, moles over kilograms. And notice how the bottom for molarity, it says solution. Molality in these guys are usually solvent. So we have to make a little bit of a difference. Molality is pretty easy to figure out. What we're going to do is we're going to turn 95 grams into moles using the molar mass of H2SO4. This is 0.969 moles H2SO4. So if we turn 5 grams into kilograms, 0.0050 kilograms, molality, little m, 0.969 moles divided by 0.0050 kilograms, moles of solute over kilograms of solvent. This number comes out to be quite large, 190 molal. So weight percent to molality, or mole fraction for that matter, not a very big thing. However, molarity, we have to do a little bit different because it's liters of solution. So if you have a molarity value and you want to go to molality, weight percent, or mole fraction, all right? If you want to go one way or the other, you need the density of the solution. Going between these three, you don't need this number at all. And that's what number 9 was all about. But on number 10, we want to go from a weight percent to a molarity. We need this density of a solution. One more piece of information.
So is that molality, weight percentage, and
Mole fraction.
Mole fraction.
That's right, yeah, that's right. Going from those three to the big M is when you need the density of the solution. How many grams total do we have of a solution in this problem on number 10? 100, that's right. Always make it easy on yourself. Chemists are lazy. I'm teaching you these things. I'm not trying to show you you're lazy. No. Anyway, 100 grams. Yeah, that's the total mass of this solution. So because we have 100 grams of solution, the 5 grams of solute plus the 95 grams of solvent, we can use this number, which I think is 1.84, yeah. 1.84 is the conversion between grams of solution and centimeters cubed or milliliters of solution. That's where the density comes in. We're trying to figure out the liters of solution. So now we've at least turned the grams of solution into milliliters, essentially. A liter is 1,000 milliliters or 1,000 centimeters cubed. This comes out 0.0543 liters. So molarity then, big M, 0.969 moles solute, H2SO4, divided by 0.0543 liters. This number, 17.8 molar. Pretty strong. So to backtrack on this problem, 95% sulfuric acid meant 95 grams of sulfuric acid, 5 grams of water, and 100 grams total. And 100 grams is the grams of solution. It's solute plus solvent. To get to molality, we took the grams of the solute and turned them into moles. We divided by 0.0050 kilograms, the kilograms of solvent, to get this big number, 190 molal. In molarity's case, we already had the moles of solute, but we didn't have the liters. So to do that, total mass of solution turned into volume using the density of the solution. You need to have density of the solution if you're going from or to molarity. Turn that into liters, moles over liters, molarity. And one final thing, almost always molality greater than, maybe equal to molarity. But most of the time, molality is much bigger than molarity. Here you can see it's 190 molal versus 17.8. If you do a calculation and molality is smaller than molarity, double check. Nathan. Sarah.
Where are you posting this?
The what?
Where are you posting this?
I may not post it if we have class, but if we don't have class, which is totally possible, I'm afraid to look outside, then I'll have it out there. Yeah. You are always welcome to come to another recitation session and listen to my bad jokes again too. That would be another option. So let's say it gets tropical all of a sudden. Thanks, Trump. Anyway, oh, sorry, no political comments. If it does get really warm and we do have class, you could always come and watch this again and stuff. I won't play with this. Yeah, won't make that. Anyway, Prophet back on. Sorry. Questions? Anything? Lay 'em on me. Okay. So, if you can get 9 and 10 down, you have the tools to conquer these solution calculations, and that's kind of the point of it. Now, 11 is kind of a sidetrack. It talks about something called part per billion. And a part per billion, like a part per million, is another type of a concentration piece. So in this one, we have silver at 28 parts per billion. And what that means is that you have essentially 28 grams of silver in a billion, or 10 to the 9th grams of water. Once in a while, someone will come into my office and say, "Hey, you want to get rich?" And I'm like, "Sure, heck yeah, I want to get rich, man." And so they start talking about seawater. And all these metals are in seawater. You can get tons of money. And I'm like, "Get out of my office." because of this problem. So let me share with you why I will tell these people to hit the road, man, because there's a problem with seawater. Now here's what they're thinking of. Seawater has gold and silver and platinum and all of these other metals that are really cool, all right? So in theory, if we took that seawater and we condensed it down, oh, there's tons of them, tons of precious metals, all right? And that's what they're seeing, and I dig that part of it. But here's the why on this problem. We're not going to do it. So on number 11, it says we want to first of all find the molality. All right. So molality is moles, in this case, of solute silver per kilogram of water. All right. So we have 28 grams of silver per 1 billion grams of water. Well, silver is about 108 grams per mole. So we can turn the grams of silver into moles. And then finally, if we want to go from kilograms, there are 1,000 grams in a kilogram, in this case of water. So the grams of water will cancel out. You get the number, which doesn't make a lot of sense at this point. 2.6 times 10 to the minus 7th molal. And this is just having fun with the units. But the next part is the part I like a lot. Now number B, it says we want to get 1.0 times 10 to the second. We want to get 100 grams of silver out of the ocean, okay? Hey, no problem. Using this relationship here, which is parts per billion, this is saying that you're going to get 28 grams of silver out for every 1 billion grams of water that you process, a billion grams of seawater. And you can then say it's about 1 gram per milliliter, so that's why 1,000 grams roughly per liter if the density is about 1. You get a number, 3.6 times 10 to the 6 liters. 28 grams of silver is not a huge amount, all right? It's worth money, absolutely, but to get this amount of silver out, 3.6 million liters. Now, if you've ever been to Albertsons, Fred Meyer's, you've seen the 2-liter containers of pop, sometimes 3 liters of pop. You'd have to go through 1.8 million 2-liter containers to get 100 grams of silver out. And that assumes 100% efficiency. We're going to talk about in Chem 223 how you basically never get 100% efficiency. You're always going to lose some silver in the process. Percent yield, we talked about in Chem 221, comes back to haunt us here. So when people say, hey, want to make a lot of money, get rich? You're going to have to go through so much freaking volume. And another thing about the ocean is that there's sometimes different density gradients. Like parts of it have more silver, parts of it have less silver. So they just their luck, they'd scoop up the easiest stuff on the surface, which probably has less silver than the stuff on the bottom. So there's problems with this. I would not advise you trying to make money off seawater. Too much volume to go through, man. Your reward is not going to be that great. So, anyway, questions? Part per million would be 28 grams of what you're looking at divided by a million, 10 to the 6 grams of water. There is also a parts per thousand, which would be 28 grams, we'll say, of whatever you're looking at divided by 1,000 grams of water. That parts per thousand is different than the parts per thousand we do in lab. Our parts per thousand is about how close the measurements are. It's a measure of precision. This is actually a type of a concentration. Parts per thousand in this context would be grams of what you're looking at divided by 1,000 grams of water. So there are 2 parts per thousands out there. We're not going to see parts per thousands in this context again, but you might in other classes. Questions? All right, so finally, number 12. We're finally getting to one of the types of solution concentrations. And number 12 is about Henry's law. And Henry's law is basically about the solubility of a gas. It equals some type of Henry's law constant K times the pressure of that gas. This is really important when it comes to like carbonating like soft drinks and beer and stuff like that. They pressurize the gas inside. the solubility of the gas in the liquid goes up as the pressure of the gas increases. So when you open up a can of fill in your favorite soft drink, you hear that psst sound. Initially your can was pressurized, so you had a lot of gas in the liquid. But as you open it up, the pressure goes down. It goes down to atmospheric pressure. As this goes down, solubility goes down. The gas escapes from the liquid. So believe it or not, this has a pretty high economic impact. Every time you hear that psh sound when someone opens up a bottle of beer or a bottle or a can of beer or soft drink or whatever, this is what it has to do. Henry's Law K is just something that's weird. A nice weird, I know, nice term for a scientist. That's, in this case, in this problem, 1.07 times 10 to the minus 6. The constants for Henry's law usually are molarity, big M, per millimeter of mercury. So you can tell the K also because it has both a concentration unit, molarity usually, and a pressure unit in the bottom. So to solve for the solubility of the gas, we need, in this case, the pressure of the hydrogen gas. And if you read through that problem, you can see it's hydrogen plus the water. Hydrogen's been collected over water. Water has a little bit of a pressure to it. So instead of using just 1 atmosphere here, or 760, you need to subtract the amount of water vapor present, the 23.8 number. So the 760 is water plus hydrogen. If you want just the hydrogen, which is what we want to subtract the water from the total pressure to get just the pressure of the hydrogen. If you do that, the solubility comes out to be 7.88 times 10 to the minus 4 molarity, which is moles per liter. And what in this context that means is 7.88 times 10 to the minus 4 moles of hydrogen per liter. Scientists are usually okay with this, but when you talk to most people, they prefer to have it in grams per milliliter, so no problem. A liter is 1,000 milliliters, and hydrogen, H2, 2.02 grams per mole. So the moles cancel, the grams are still left, the liters cancel, you've got grams per milliliter, 1.59 times 10 to the minus 6, grams per milliliter. So what this number says is that in a milliliter of water, in a milliliter of water, you're going to have 1.59 times 10 to the minus 6 grams of hydrogen in solution. As the pressure goes up, the solubility of your gas will go up too. So you can really pressurize these things if you want. Again, soft drink industry, McMinimans, they will pay attention to things like this. Yeah.
What number is that above the mole on the last part?
This part right here? Yeah. This is the molar mass of H2, Connor.
Okay.
So because it's H2, 2.02 grams per mole is what I wrote there. Yeah. By all means, ask that kind of stuff. Rebecca?
Will we ever use the temperature values given in that one?
Oh, the temperature affects the Henry's constant. That's a really good question. In the Handbook of Chemistry and Physics, you can look up these things as they change with temperature, just like density. Will you ever have to use it for a Henry's Law question? No. I'll give you one Henry's Law constant. You can just ignore the temperature. Really good. But again, in the same class that Nathan's going to take where they talk about differences, solid, liquid densities on vapor phases, you can actually figure these things out too. Excellent. Prof. I'm still on. Questions? Okay. Number 13. Number 13 is an example. Sorry, studio audience, you're probably dizzy and throwing up at this point. Anyway, all right. Number 13 is an example of what's called Raoult's Law. I'm probably not saying it right, I'll be honest. But what it's all about is it talks about the vapor pressure, VP, of the solvent in the solution. And what happens is the vapor pressure of the solvent in the solution is equal to the mole fraction of the solvent. So again, chi here is the symbol for the mole fraction. It's the mole fraction of the solvent times the vapor pressure of the pure solvent. If you see that little zero sign, the superscript 0, that means that you have a pure solvent. So let's say we have water, and on number 12, at that temperature for the problem, the vapor pressure was 23.8 millimeters of mercury. 23.8 would be like the vapor pressure of pure water, all right? It's a number when you have just water. But what Raoult's law says is that as you start adding a solute, the mole fraction here is actually going to decrease. And we'll see this here in a little bit. So when you have a smaller number times the vapor pressure, which is just a constant, the vapor pressure of the solvent in the solution will be less. So Raoult's law is sometimes called vapor pressure depression because the solvent particles are unable to go into the gas phase as easy. Let's say I said, that's it, screw it, I'm out of here, all right? I just walk out to the door, I can go right here. But let's say that Ellie's right here, and she goes, no, Russell, you gotta help us finish the problem. I said, thank you for being my model. Oh, it's gonna be harder for me to go around her, right? She's like blocking me. Not really, but really. She's like the solute, all right? She's blocking me, the solvent, from getting to the vapor phase and escaping. Seems kind of appropriate today, but no. Oh man, my jokes are really bad today, I'm really sorry. So, Raoult's law is like the solvent trying to get into the gas phase, going from liquid to gas. And normally, it's just an easy transition. But if you have a solute there, something to block it, it lowers the way that the liquid goes into the gas phase. So the vapor pressure over a liquid will go down in the solution relative to the pure solvent. So over pure water, maybe we would measure 24 millimeters of mercury. We put in some kind of solute, it'll go down maybe to 20 millimeters of mercury. We can use Raoult's law to talk about that. Questions on that part? Okay, so on number 13, we have the vapor pressure of the pure solvent. It's the 22.4 millimeters of mercury. That's the vapor pressure of water at this temperature. And again, temperature won't play a factor with this either, Rebecca. But that's the pure vapor pressure when only water is there. And this reflects how easy it is for water to escape, all right? But we have solute blocking the solvent. So that's when we need to talk about mole fraction. Mole fraction is moles, all right? So it says we have 9 grams of urea, and it is in 10 milliliters, which is 10 grams if the density is 1.0, 10 grams of water. So we're going to turn both of these now into moles. So urea has a molar mass of 60.06 grams per mole. Water has a molar mass 18.02 grams per mole. So the urea, 0.150 moles. The water, 0.555 moles of water. So, mole fraction of solvent, chi solvent, is going to, in this case, be moles of water divided by moles of water plus moles of urea. On number 9, we were looking at mole fraction of solute. So it was like moles of KNO3, the solute, divided by moles of KNO3 plus moles of water. But for Raoult's law, it's mole fraction of the solvent. So if you do this, if you take 0.555 and you divide it by 0.150 plus 0.555, the mole fraction comes out to be 0.787. And that is what we want to put in right here. That's the mole fraction of the solvent. We're multiplying it by the vapor pressure of the pure solvent. So 22.4 times 0.787, 17.6 millimeters of mercury. That's the vapor pressure of water in the solution. So normally, water has a vapor pressure, the amount of pressure of liquid able to go to gas, 22.4. But the solute is again blocking the water, so the pressure is much less. All right, it's less, the vapor pressure of the solution is less than the vapor pressure of the solvent. Questions? Okay. 14, 15, 16, and 17 all have a very similar type of problem. And it's all related to something which looks like this. Delta T equals K times M and sometimes I, which we'll talk about later. But at first, let's just talk about delta T equals K times M. Raoult's law leads us to what's called freezing point lowering and boiling point elevation. And a solution is going to boil higher than the solvent it comes from, and a solution will freeze lower than the solvent it comes from. So again, back to good old water, it boils at 100 and freezes at 0. I want some pasta, he says. So when I make pasta, I usually throw some salt in the water. It's more for spice than anything. However, salt is acting as a solute. And the salt will block a little bit the water's ability to boil. So boiling points of solutions are higher than the boiling point of the pure liquid they come from. So if water boils at 100, if you put in some salt, maybe your boiling point now will be like 102 degrees. It's not a huge difference, but there's some pretty powerful consequences of this. So solutions' boiling points are higher, and the same thing happens when you freeze things. Now, like if it's gonna get icy, sometimes now they'll put like this de-icer stuff on the road. It's basically a salt solution. Salts will lower the ability of a solution to freeze. So if water freezes at 0, pure water, in a solution, maybe the water would freeze at like -5 degrees. It's a little bit lower than it usually does. And it all has to do, again, with the solute blocking the solvent. In boiling, it keeps this liquid from going to the gas phase. In freezing, it keeps the liquid from becoming a solid. These blockers, these solutes, are actually really important in understanding what the solvent is doing. So all these problems are going to be really similar, excuse me. They're going to be delta T equals K times M and sometimes I, although I'm going to forget it. K is going to be a constant, all right? K is going to be a freezing point or a boiling point constant, nothing you ever have to memorize, all right? I'll give you all of these. Little m here is molality, and this is why we're studying these crazy units a lot, because molality is what affects a lot of these things. And delta T will be the change in the temperature. So if water normally boils at 100 and our solution's 102, delta T would be 2 degrees. Okay.
If there is an I, what would that be?
I is called the Van Hoff factor, and we will use it, but if you give me just a little bit longer, we don't need it in this problem. Most of the time, drop that off, Rebecca, we won't need Van Hoff, so I'm kind of putting it on the back burner, but it does pop up here in a little bit. So Rebecca's right, there's this little I, which I haven't talked about yet. I will here in a little bit, I promise. Okay, so remembering the I is just something we're not going to worry about right now. Delta T is a question about caffeine in benzene. Never enough caffeine. Anyway, 14. We're trying to figure out the change in the boiling point temperature. All right. Now, normally caffeine boils at 80.10 degrees. So we're going to first calculate a delta T for the solution. And whatever that number is, we're going to add it to 80.10 to get a final temperature which is higher than the solution, than the pure benzene would be. So K is a number that's given. It's 2.53 degrees Celsius per molal. It's a weird kind of a unit, and again, you don't need to worry about any of those. I would give them to you. Now, molality is moles of the caffeine, the solute, divided by kilograms of benzene, the solvent. So I need to figure out what both of these are before I can solve for molality. I have 0.755 grams of caffeine, And a mole of caffeine, which I'm sure you all have memorized, not 190, sorry, nerdy chemistry joke. 194.2 grams per mole is the molar mass of caffeine. And I'm going to divide that by 0.0956 kilograms. So if we had 95.6 grams of benzene, that would be this many kilograms. So moles of caffeine over kilograms of benzene, the molality, 0.047 molal. So if I put that up here, I now have my molality, this weird K thing. Delta T will be 2.53 times 0.0407, and it comes out to be 0.103 degrees Celsius, a pretty small number. So if benzene normally boils at 80.10, this is the normal boiling point, I'm going to add this number to the benzene's boiling point. Benzene in the solution will be raised by 0.10 to 80.20 degrees Celsius. These delta T's are pretty small. It doesn't raise the solution that much, but it does raise it. And this is something we can measure here at Mount Hood. This is something we would have been measuring if we would have done the lab today, but we're going to do the take-home one instead. And there's some cool things you can get out of it. Any questions? All right. Now, 15 is a similar kind of problem. It's another delta T equals K times M. I'm still ignoring I, but this time it's for freezing instead of boiling. So while 14 was about boiling, 15 is about freezing, but the process is very, very similar. All right, it's going to be something. In number 15, instead of finding delta T, we want to solve for molality, and molality will lead us to grams of solvent, I believe. So in number 15, we have this ethylene glycol. We want our solution of our water ethylene glycol to have a freezing point 15 degrees lower than normal. So normally water boils at 0. We want to have our new freezing point negative 15. Now, the only important thing to realize about freezing point is that initially you might see a negative delta T. You might see, for example, a negative 1.86. I don't care if you use negatives or positives here. I do want you to realize that molality is a concentration. And in chemistry, we never have negative grams, negative moles, negative volumes, stuff like that. So molality must be a positive number, all right? You can use a negative K if you want. You can use a negative delta T, that's fine, but your molality must be a positive number. Different books will have different ways of doing it. Just make sure your molality is a positive number, because you can't have negative mass in chemistry. Sometimes that's a disadvantage, but here, honestly, it's kind of an advantage, so. All right, so this number, 8.06, is the molality. It's the moles per kilogram. Nice job. This person took the moles of the ethylene glycol and turned it into grams. They had this many grams of ethylene glycol per kilogram. We have a 5 kilogram mix, so the kilograms cancel. 2,500 grams of ethylene glycol would be what you'd need to add to 5 kilograms of water to make your solution freeze at negative 15. So if you lived in the Midwest or something where things are colder than they are here, and you wanted your radiator to not be a freezing point of 0 but negative 15, add 2.5 kilograms to your 5 kilograms of water, your solution will be colder. Any questions on that? Okay, so 14 and 15 pretty similar. 16 and number 17 are going to be pretty similar. So over here on the side, I'm going to put a column and I'm going to have the corresponding values for number 17. Now 16 and 17 are why we pay so much attention to these. and it's another mechanism to find the molar mass of a compound. So just like having the molar mass of a volatile liquid was important, these are even better because there's a lot more opportunity to find a molar mass if you use freezing point or boiling point. Now, number 16 is a boiling point question, and number 17 is a freezing point question. But the process is really, really similar. The first thing you want to do on number 16, your solution normally boils here, now it boils up to this point, so you want to find the delta T, and you want to divide it by the K that you're given. So this person in the boiling point, here's delta T, here's the K value. They solved for the molality, which is the moles of the solute per kilogram of solvent. Because we used 2.5 grams, 25 grams of solvent, if you take the moles per kilogram and you multiply by the kilograms of solvent, so 0.025 kilograms times moles per kilogram, the kilograms cancel, you'll be left then with so many moles of solute, which is where this number came from. And if this many moles came from this many grams, the last thing to do, solve for the molar mass. So grams of solute divided by moles of solute, nice job, about 180 grams per mole. So this compound, this BHA, which who knows what the heck it is and stuff, BHA has a molar mass of 180 grams per mole. And even though we have cool instruments that can tell molar masses, you never know for sure if your instrument is calibrated just right. This is a nice way to double check. That's okay. 17 is not only similar to 16, this is also a great question regarding the take-home lab. Because in the take-home lab, the goal is to find the molar mass of an unknown compound. So the process on number 17, which is similar to lab, which is similar to number 16, do the same thing. You're first going to find a delta T, all right? And delta T for that one, they give you a number 17, 0.197. That's the difference between where the solution freezes and the pure solvent freezes. It's a pretty small number. But the next thing you want to do, solve for the molality. And molality will be delta T over K. Just like up here it was delta T over K. Molality has to be a positive number. Molality at number 17, 0.106 molal. Once you have the molality, multiply by the kilograms of solvent to get the moles of solute. So when you do that on number 17, moles of solute of aluminon, which we'll use in Chem 223 by the way, 0.00530 moles. So again, if we take this 0.106 molal and multiply by the kilograms, that's where this 0.00530 comes from. And then the last step on number 17, molar mass, grams of solute divided by kilograms of solvent. On number 17, that would be 2.50 divided by 0.00530, 472 grams per mole on number 17. So even though 16 and 17 and 14 and 15 were different processes, very similar in how you approach one to the other. And if you can do 16, you can do 17, same kind of problem. And if you can do 17, you can do the lab take-home. All right, last thing. I still haven't talked about Van Hoft, and I apologize to Rebecca, but we're gonna do it now. The last one is a different process. It's osmosis. All right, and osmosis gets this thing right here, and I am going to put the I in there. Now, osmosis is the fourth colligative property, which means the fourth property of solutions. Pi is what they call osmotic pressure, and it gets either atmospheres as usual, sometimes other things, but P is pressure with gases. Pi is a pressure, but this is a pressure of solutions. And if you've ever studied biology and stuff, osmosis is so important to cells. It allows water to go in and out of cells, and you have to have them at the right concentration, stuff like that. So this is a pressure. It's given the Greek symbol pi just to make it different. This isn't 3.1416, the math pi, all right? This is a different kind of pi. But anyway, T is the Kelvin temperature, and make sure you use Kelvin temperatures for T. R, we're back to 0.082057. This is the good old gas R here we're using. So this one we will use 0.082057. C is molarity. So after dealing with molality and weight percent and mole fraction, we're back to a concentration unit again, which is molarity, the big M. And finally, I is what they do call the Van 't Hoff factor. And this is a really interesting piece. All of the examples we've seen so far from Raoult's law up have been with covalent molecules, molecules with shared electrons inside them. Van 't Hoff factor is useful when you have ionic compounds. So all of the versions we've done so far, and why I didn't address Rebecca's questions yet, is because every one of the solutes and solvents we had were covalent. Electrons were being shared. If you have a covalent molecule, your Van 't Hoff factor is just equal to 1, so it's like it doesn't appear. But on number 18, though, we need to think about this, because on number 18, we have sodium chloride. Now, what happens when you place sodium chloride in water? Yeah, it dissolves. It dissolves really well. You stir it up and the solids go away. Do the sodium chlorides, do they stay as NaCls? No. Right up. They dissociate. They break up into Na pluses and Cl minuses. So NaCl breaks up into Na plus and Cl minus. So notice how one piece, if you will, breaks up into two pieces. The Van 't Hoff factor is only used for ionic compounds, and it reflects the number of ions in solution. So for sodium chloride, one piece goes into two pieces. I would be 2. Let's say that we had magnesium bromide. It breaks up into magnesium ions and 2 bromide ions. What do you think the I factor would be for this one? 3. That's right. Well done, guys. 1 magnesium, 2 bromides, I factor would be 3. Okay? But again, acetone is an example of a compound that does dissolve in water, but acetone is covalent bond. So anytime you've got nonmetals, acetone, ethanol, caffeine, whatever, all of those have just I equals 1. So this is why I've been kind of putting it off, because most of the examples we're going to see do have covalent bonds, and we don't need to worry about Van 't Hoff. But if you've got one of these ionic compounds, like sodium chloride in number 18, you will have an I factor other than 1, and then you have to put it in. Okay. All right, so going back then to number 18, we want to solve for the osmotic pressure, pi equals ICRT. And we're trying to find the actual the pressure value. So I is going to be 2. Because again, sodium chloride breaks up into Na plus and Cl minus, 2 pieces. Concentration, moles per liter, 0.154 moles per liter is just what you put in right there. R, 0.082057 is the R. And Kelvin, so make sure you turn Celsius to Kelvin, also multiply by 310 Kelvin. So in your calculators then, 2 times 0.154 times 0.082057 times Kelvin, 310, 7.83 atmospheres. And if you think about this, that's a pretty significant pressure, because one atmosphere is kind of what we're used to as humans. And in our cells, you can have these pretty large pressures, 7, 8 atmospheres, pushing water around and stuff. Anyway, this is how people can calculate the actual pressure in the cell solution, stuff like that.
Just a question about the sig figs.
By all means.
So in the molarity, there are 3 sig figs, but in the Celsius also there are only 2. And why did you go with 3?
Cool. When you take Celsius and you turn it to Kelvin, yeah, you cut it off so it becomes a 3 sig fig number. That's right, Rebecca, good thing. That's a really good question. Other questions? Okay. So again, what we're going to do today is, first of all, just about done. First of all, what we're going to do is I want you to turn in your problem sets. You give me a couple minutes and stuff, I will grade it, and I will return that with your work from last week in just a couple of minutes. But at the very least, what I'd like you to do, all right, please help me erase the chalkboards. I'm going to have 2 piles up here. One of them is the take-home lab, which is right here, and the other one is the take-home quiz. So grab each of these and stuff before you leave. Turn in the problem set. And again, if you give me just a minute or so, I'll grade it, return your stuff. No lab today. Have a good day. Stay warm. See you soon.